Hello, in this lesson we're going to learn how to use fundamental trigonometric identities. These identities are some of the most important tools in trigonometry because they allow us to simplify expressions, evaluate functions, rewrite formulas, and solve more complicated problems. As you continue into higher level mathematics, especially calculus, you'll use these identities frequently. Let's get started. In this lesson, we'll focus on recognizing and using the fundamental trigonometric identities. We'll begin by reviewing the major identities that every trigonometry student should know, including reciprocal identities, quotient identities, Pythagorean identities, cofunction identities, and odd and even identities. Then we'll see how these identities can be used to evaluate trigonometric functions, simplify expressions, factor expressions, rewrite formulas, and perform substitutions. The goal is not to simply memorize the identities, but to understand when and how to use them. Let's begin by reviewing the fundamental trigonometric identities. The first group is the reciprocal identities. These tell us that the sine and cosecant are reciprocals of one another. Cosine and secant are reciprocals, and tangent and cotangent are reciprocals. The second group is the quotient identities. These express tangent as sine divided by cosine, and cotangent as cosine divided by sine. The third group is the Pythagorean identities. These come directly from the Pythagorean theorem and are among the most commonly used identities in trigonometry. Notice that the first identity can also be rearranged to solve for sine or cosine when the other function is known. These alternative forms are especially useful when evaluating unknown trigonometric functions. This slide introduces three additional categories of fundamental identities. The first group is the cofunction identities. These relate trigonometric functions whose angles add up to 90 degrees, or pi over 2 radians. For example, the sine of an angle's complement is equal to the cosine of the angle. Next are the odd identities. Notice that when we replace the angle with its negative, the value of sine, tangent, cotangent, and cosecant changes sign. Finally, we have even identities. Cosine and secant are even functions, which means their values do not change when the angle is replaced by its negative. These may seem like a lot to remember at first, but with practice they become familiar and extremely useful. You'll use them repeatedly in both trigonometry and calculus. One common application of trigonometric identities is finding all 6 trigonometric functions when only partial information is given. In this example, we're told that secant of u equals -3/2 and that tangent of u is positive. We begin by using the reciprocal identity to find cosine. Since secant is the reciprocal of cosine, cosine must be -2/3. Next, we use the Pythagorean identity to find sine. Substituting the value of cosine into the identity allows us to solve for sine squared. After simplifying, we find that sine is either positive or negative square root of 5 over 3. At this point, we must determine which sign is correct. That's where the quadrant information becomes important, which we'll discuss in the next slide. Now let's determine the correct sign for sine. We're told that secant is negative and tangent is positive. Since secant has the same sign as cosine, cosine must be negative. And because tangent is positive, sine and cosine must have the same sign. The only quadrant where both conditions are true is quadrant 3. In quadrant 3, sine is negative. Therefore, we choose the negative value for sine. Once we know both sine and cosine, finding the remaining trigonometric functions is straightforward. We use the quotient identity to find tangent, and then use reciprocal identities to find cosecant, secant, and cotangent. This example shows how identities and quadrant analysis work together to determine all 6 trigonometric functions from limited information. Let's look at simplifying a trigonometric expression. The key idea is to look for common factors and opportunities to use these identities. Here we factor out a sine term and then recognize the expression 1 minus cosine squared. Using the Pythagorean identity, we replace that quantity with sine squared. After simplifying, the expression becomes negative sine cubed x. The second part of the slide focuses on factoring trigonometric expressions. Notice that these problems are treated very much like algebra. The expression secant squared x minus 1 has the form of a difference of squares and factors accordingly. The second example involves the quadratic expression in tangent. Just as we would factor a quadratic polynomial in algebra, we factor this expression using tangent as the variable. The important lesson here is that many trigonometric expressions can be simplified using familiar algebraic techniques together with trigonometric identities. Let's continue with another factoring example. This time we start with cosecant squared x minus cotangent x minus 3. The expression doesn't immediately appear factorable, so we first use a Pythagorean identity to rewrite cosecant squared x as 1 plus cotangent squared x. After simplifying, the expression becomes a quadratic in cotangent, which can then be factored. The second example illustrates how identities can be used to prove an equation. Our goal is to show that the expression on the left simplifies to cosecant t. We begin by replacing cotangent with cosine divided by sine using the quotient identity. Next, we combine the terms in a single fraction. Applying the Pythagorean identity allows us to replace sine squared plus cosine squared with 1. The resulting expression becomes 1 over sine t. Finally, using the reciprocal identity, we recognize this as cosecant t. Whenever you're proving an identity, the strategy is usually start with one side and simplify it until it matches the other side. Now let's look at adding trigonometric expressions. The process is very similar to adding ordinary fractions. We find the common denominator, combine the numerators, and then simplify. After applying the Pythagorean identity and canceling common factors, the expression simplifies to cosecant x. The second example focuses on rewriting an expression. We start with cosine squared x divided by 1 minus sine x. Using the Pythagorean identity, we replace cosine squared x with 1 minus sine squared x. Then we factor the numerator as a difference of squares. This creates a common factor that can be canceled. After simplifying, we're left with 1 plus sine x. Again, notice how often algebra and trigonometric identities work together. Our final slide introduces two additional applications. The first is trigonometric substitution. We're asked to rewrite the square root of 9 minus x squared using the substitution x equals 3 sine theta. After substituting, we factor and then apply the Pythagorean identity. This transforms the expression into 3 cosine theta. Trigonometric substitution is an important technique and that becomes especially useful in calculus. The second example involves logarithms and trigonometric identities. We begin with the sum of two logarithms. Using the product of logarithms, we combine them into a single logarithm. Then we replace cosecant and tangent with equivalent expressions using reciprocal and quotient identities. After simplifying, the result becomes a natural logarithm of the absolute value of secant theta. This example highlights how trigonometric identities often appear alongside other mathematical concepts, including logarithms. This concludes our lesson on using fundamental trigonometric identities. Thank you for watching, and I'll see you in the next lesson.